For decades, automotive safety was an exercise in pure physics and metallurgy. Engineers obsessed over stress testing brake rotors, steering columns, and axles to ensure they wouldn't snap at 60 miles per hour. The entire design philosophy centered on preventing a physical machine from breaking down. Today, a modern vehicle operates as a rolling supercomputer. Code, radar arrays, and redundant electrical systems have engineered away almost every traditional mechanical fault. We've reached a point where the car itself is rarely the cause of a malfunction. Yet cars with perfectly intact components and fully functioning sensors still end up in collisions. Eliminating mechanical flaws has failed to eliminate the danger. Picture a vehicle cruising down a dark, rain-slicked highway. The onboard radar tracks the lanes flawlessly, the braking system is primed, and the engine hums along without a single error code. Meanwhile, the person in the driver's seat is leaning back, completely tuned out. The sensors might lose sight of the painted lines for a fraction of a second, handing control back to a driver who isn't looking. The technology is working exactly as designed, but the scenario still turns lethal because the human pushes the system past its operational limits. This chart illustrates a new engineering standard created to map these exact blind spots. It's called SOTF, or the safety of the intended functionality. At the center is the known safe condition. Surrounding it is an expanding area of unknown risk, generated by unpredictable environments and human interaction. Meeting this standard forces a shift in the engineering roadmap. The focus has moved from protecting the car against physical hardware failure to shielding the system from the documented cognitive biases of the human operator. When we turn over steering and braking to a computer, our own psychology becomes the weakest link. In the engineering world of autonomous driving, human error is treated with the same analytical scrutiny as a mechanical breakdown. To analyze exactly how a flawed mind derails a perfect machine, SOTIF engineers break human cognition down into a three-step timeline: recognition, judgment, and action. The breakdown usually begins at the first node, recognition. The dashboard flashes an alert, but the driver is distracted by a text message or simply zoning out. The sensory information never registers. The driver misses the cue. Even if the driver sees the warning, the failure can cascade into the next step, judgment. Here, a person incorrectly assumes the car's autopilot can handle a sudden downpour or a fading lane line. They build a flawed mental model, trusting the system to survive conditions it was never programmed to navigate. Finally, this leads to an action error. Startled by a sudden warning, the human panics. They stomp the accelerator instead of the brake, yank the wheel too hard, or freeze and do absolutely nothing at all. A processor that calculates millions of variables per second is rendered useless by a 3-second delay in human cognition. This timeline of errors is often an unintended side effect of the technology itself, a psychological trap known as automation complacency. When an autonomous system drives perfectly for hundreds of miles, it trains the human brain to relax. The reliability of the code convinces the driver that monitoring the road is a waste of time, prompting them to abandon their oversight. This sets the stage for mode confusion. The vehicle encounters an unexpected obstacle, like heavy fog, and silently downgrades its capabilities. But inside the complacent driver's head, the system is still operating at full capacity. The car's reality and the human's mental model have completely disconnected. In that window of time, the car has handed responsibility back to the human, but the human hasn't realized they need to take it. For those few seconds, a 2-ton vehicle is rocketing forward at highway speeds, and neither flesh nor code is actually in control. We arrive at a bizarre engineering paradox. By making automotive technology incredibly convenient and smooth, we actively stripped away the driver's attention. The pursuit of a reliable machine made the human more dangerous. Solving this paradox requires an inversion of how we design vehicle interiors. Since human attention spans are a known point of failure, the machine must be programmed to manage the human operator. This is where driver monitoring systems, or DMS, come into play. They act as a dedicated countermeasure to complacency, using infrared cameras and AI to watch the driver as closely as the radar watches the road. These systems continuously track head posture and eye position. The moment a driver looks away or their eyelids droop, the system calculates that a recognition error is forming. It catches the human failure before it starts. To snap the driver out of mode confusion, the car initiates a carefully escalated sequence of sensory feedback. It starts with a sharp visual alert, escalates to a piercing audio chime, and finally vibrates the steering wheel to force the human back into the loop. The most advanced vehicles on the road today have effectively turned their sensors inward. They analyze the driver's biological state as a primary safety variable, mirroring the attention they pay to the asphalt and traffic outside. The principles of SOTIF mark a move toward truly collaborative engineering. The vehicle has evolved into an active environment that anticipates and bridges the gaps in human psychology. True safety on the road requires a constant closed-loop dialogue. The car manages the limits of the human's attention, and the human steps in to manage the limits of the software. It's a continuous handoff between imperfect flesh and precise code. The ultimate success of an autonomous system lies in how seamlessly it integrates with the unpredictable humans inside, rather than its ability to function in total isolation.